All right, so in these notes, we're going to go ahead and talk about graphing logarithmic functions. And logarithmic functions are actually the inverse of exponential functions, which we will learn more about tomorrow. So when I say inverse, I mean like multiplying and dividing. Those are inverses of each other. Adding and subtracting are inverses of each other. If we have an x squared function, the inverse of that is a square root function. And so now we're going to learn about log functions, and log functions and exponential functions are inverses of each other. And if you guys recall, when you find an inverse, you just trade the x and the y coordinates. If you're looking at points or if you're looking at the equation, you trade the x and the y values and then you solve for y. So here, if we want the important information, we don't necessarily have to memorize a new set of information. We just have to remember the important information from an exponential graph. So if you guys recall, the exponential graph we had was y equals b to the x. And we said if you plug 0 in, b to the 0 is 1. And if you plug 1 in, b to the 1 is b. And that there was no way to make that 0 out, and so we had y equals 0 as a horizontal asymptote. So if this is the exponential information, then we would say we're going to do the inverse of all of that, and so we're going to flip all those x's and y's. So this would be 1, 0. This would be b1, and then instead of having a horizontal asymptote at y equals 0, we're going to have a vertical asymptote at x equals 0. So we have vertical, and then we have the point 1, 0, and then it would be the base 1, and so maybe we could have a base of 3 or a base of 10 or whatever. I'm going to go ahead and give it a base of 3. And then there's our graph right there. Okay, so let's go ahead and learn how to graph the first one. So we're going to start off exactly the same way. Actually, I'll go ahead and write this out. Y equals A times log base b of x minus h plus k. So when you look at this, the inside of the function is going to be whatever's inside the parentheses. The outside of the function would be the number on the end. You can have a number in front of the log. And then the base of the log is going to be the number that we use for b, for our base. All right, so first I'm going to go ahead and look at this. I have a base of 2. And then I'll go ahead and find my transformations. I have a reflection over x, left 1, up 5. So I'm going to start with those points 1, 0, base 1, x equals 0. So reflect over x means the y coordinates get multiplied by a negative 1. So just multiply by negative, multiply by negative. We're going to shift to the left 1, so 0, 1, vertical asymptote shifts to the left 1. So if you guys recall, when we were doing our exponential notes, the number on the end was the asymptote. Now, since we're thinking kind of like the opposite of that, because we're doing the inverse of exponential, then the inside is going to give us the asymptote this time. All right, and then it said up 5, so 0 plus 5, negative 1 plus 5. All right, so I've got a vertical asymptote at negative 1. And I've got the point 0, 5 and 1, 4. And so that means that the graph is going to look like this. Okay, and then we have all the normal things that we're going to find, right? So I'm going to look for my domain and range. So domain is how far left does the graph go, range is how far y does, up and down does the graph go. So left and right, we're going to say from -1, that's where it stops, to positive infinity. The range is up and down, and so it goes down forever and it goes up forever, so -infinity to positive infinity. If we look at increasing and decreasing intervals, we're going to notice that just like the exponential graphs, it's only going to do one or the other. So if I put my little stick figure guy right here, he's going to be decreasing. The x-coordinate right here would be -1. Even though it's an arrow, it's just going to get really, really close to that -1. It's never going to cross it. Over here, the x-coordinate is positive infinity, and so this is decreasing from -1 to infinity, but it is never going to increase. I'm going to look for my x-intercept and y-intercept. I actually already know what my y-intercept is. It's that 0.05. So I can go ahead and graph this. And I would like for you guys to be graphing this with me because it's going to be different to graph depending on what calculator you have. So if you have a newer calculator, you're going to hit the math button and go up, up. Math button up, up to log base. And I forgot to put my negative in there, so I'm going to go ahead and clear it and do that. So negative, math, up, up. So log base 2 of x plus 1 with a plus 5 on the end, right? If you do not have this type of calculator, then you should write this off to the side. Y equals negative, and then you're going to do log of x plus 1 divided by log of 2 with a plus 5 on the end. Sorry, that looks kind of terrible. So we'll go ahead and show you that these two things look the same. It doesn't matter. So this is what our log graph looks like, and that matches what we drew. And you'll notice on this that if you were to just graph this and not know that there was an asymptote there, it'd be really easy to miss it. You'd think that maybe the graph just stopped, and the graph didn't stop. It's that your calculator has a hard time doing vertical lines. And so since this curve has gone almost completely vertical, your calculator just cuts it off. And we know that it shouldn't have cut it off. It should have still been there. So if I go ahead and graph this again, but typing it this way, then on an older calculator, I would actually use the log button. So negative log button of x plus 1 divided by log button of 2 plus 5 on the end. And you'll notice that when I graph it, it's the exact same graph. So it doesn't matter how you plug it in. I would say if you have a newer calculator, do the easier one, but older calculators can do it just fine. Okay, so we're going to go ahead and look for the x-intercept. I can tell that it's going to cross. It's just going to take some more time. And so this is the right of our screen. So if I hit the window button, I need my x max to be a bigger number. So I could try like 20. And it looks like I got a little bit closer, but it still hasn't crossed yet. So I'll try 30. And there we can see, oh, it looks like it almost crosses, maybe 40. There we go, we can see that it definitely crosses. So I'm going to do second trace, option number 2. I'm going to do my left bound and right bound, so I'm going to call this my left bound. I'm watching my y values to see when they get negative. There we go, so it means it crossed over the line. My right bound. So my x-intercept is 31, 0. So sometimes you might have to change the window so you can see everything. Is this graph continuous? Yes. Is there a max or a min? Is there a mountaintop or a valley? No. Or none, I guess. Our end behavior, we're going to say as x goes to negative infinity, as x goes to positive infinity. So as x goes to negative infinity, I'm going to look at the left side of the graph, but x doesn't go to negative infinity. It stops at the asymptote. So I'm going to say y is undefined. You can't plug a big negative number into the problem. It doesn't work. As x goes to positive infinity, the y value is just going down forever. So y goes to negative infinity. Okay, let's do another example. So for this one, again, we want to know what the base is in our transformations. And so the base is 4. We have a vertical stretch of 2, and it goes to the right 3 and up 4. So I have the point 1, 0, base 1, x equals 0. So I've got my vertical stretch of 2. That means I'm taking the y coordinate and multiplying it by 2. So 0 times 2 is 0, 1 times 2 is 2. Then I will shift to the right 3. And again, we'll remember that the number on the inside is what gives us our vertical asymptote this time. And then it says that we've shifted up 4. So I have a vertical asymptote at 3. And we have the point 4, 4 and 7, 6. And so that's what our graph looks like. So the domain, the furthest that this graph goes to the left is 3, and it goes to the right forever. It goes down forever and up forever. If we put a little stick figure, he would be walking uphill, that's increasing. The x-coordinate over here is a 3. The x-coordinate of a right arrow is an infinity, so increasing from 3 to infinity, decreasing never. X-intercept, y-intercept, we know that for the y-intercept there'd be none because that asymptote is keeping the graph from crossing the y-axis. But the x-intercept, we can see it's going to be some number that's a little bit bigger than 3, so I need to go ahead and graph this. So again, you can hit the math button and go, oh, but I should have typed my 2 first. So 2, math button, up, up, get your log base 4 of x minus 3 with a plus 4 on the end. That's the new calculator way. Or if you have an older calculator, we're going to type y equals 2 log button x minus 3 divided by log button of 4 plus 4. So 2 log of x minus 3 divided by log 4. So each time I have the log there, I was hitting the log button with a plus 4 on the end. And hit graph. And it looks like what I drew, but because it's having a hard time with that vertical asymptote, it's not crossing the x-axis. I'm going to go ahead and change my window back to normal. Okay. So we have 2 different options for how we can find this. If you try to do second trace, option number 2, and you try to like scroll left and right, the calculator is not going to let you do left bound, right bound. Like you just can't do anything on the left side. It just won't do it for you. So if you're gonna do it that way, you actually have to type in your left bound and right bound. So I can see that it really is there. There is an x-intercept there, and I know that it's between the vertical asymptote and the number 4. So I could go ahead and I could just type 3 for my left bound. Type 3 for my left bound, type 4 for my right bound, and the calculator will find it for me. The other way you can do it if you want to be able to scroll for your left bound and right bound is you have to change your window. So if we look at what the window is already, we could say we want it to be 3, and then it doesn't have to go up or down a ton. So maybe I could say left and right go from like -1 to 4, and then for up and down maybe like -2 to +2, just like really zooming in on that part where it crosses the x-axis. So now I can see that it really does go through because I zoomed in. And so now I could do my left bound and right bound. Let me get there. Okay, so now I can do left bound, right bound, and get the answer. So you can do it either way, it just comes down to what you're more comfortable with. Okay, so we have those. We know that the graph is continuous. We know that there's no max or min, no mountaintops, no valleys. For the end behavior, as x goes to negative infinity, the y value is going to be undefined because it doesn't go to negative infinity. The graph stops. As we look to the right of the graph, as x goes to positive infinity, the y value is going to be going up forever, so y is going to positive infinity. Sorry, the sun is shining through the window. There we go. All right, so very similar to what we did yesterday, or today, I guess, but slightly different. So if you look at these, you could actually compare these answers to what you saw when you were working on exponential functions, and you're going to notice that some of the things have traded. So for instance, when we were doing exponential functions, the domain was always negative infinity to infinity, and it was the range that changed. But now they're opposite. Now the range is negative infinity to infinity, and the domain is the one that's going to change. So like that's a little different than it was last time. You'll notice that last time with the end behavior, we did have one of the end behaviors going to infinity, but the other one went to a specific number. So this time one's going to be undefined because the asymptote's going the other way. So you'll notice there's like some things that are similar, but definitely some things that are different too.